From the Library of Congress in Washington, D.C.
Good morning, everyone. I'm Josh Sternfeld, the Senior Program Officer with the National Endowment for the Humanities Division of Preservation and Access. First, I want to thank Aaron Engel and Bill and the entire conference committee for their tremendous support for helping to organize this panel today. So why are we here today? Well, from emerging fields such as digital forensics, to press coverage of massive server farms constructed by Apple, Google, and other major corporations, we are developing an acute social awareness of the materiality of data, and consequently, the environmental costs for preserving our digital heritage. The question remains whether we can achieve mutually beneficial compatibility between stewardship of our digital collections and stewardship of the planet. The formula for achieving greater environmental sustainability is relatively clear-cut. A reduction in energy and resource consumption effectively can lead to greater cost efficiency. But models for how we arrive at that endpoint can be enormously varied, complex, and with roadblocks set all along the entire pathway. As will become apparent from the presentations by our esteemed panelists, a comprehensive examination of the topic requires an interdisciplinary approach that engages multiple interest groups, including preservationists, IT specialists, administrators, computer engineers, environmentalists, and many others. Any solutions would likely also challenge our shared notions of best practices surrounding digital stewardship, such as selection, curation, acquisition, and even our perception of long-term preservation and access. While we hope to cover a lot of ground with our session today, its success depends on continuing the discussion throughout this conference and beyond. For that reason, we have included a brief abstract, as Aaron indicated, in your registration packet, complete with suggested readings to kickstart further inquiry, and that abstract is also posted online. And we hope to see the conversation picked up in social media. We have a hashtag designated Green Dig Prez, as well as various websites and blogs. So, allow me now to introduce our three presenters. Starting us off will be David Rosenthal, who is perhaps best known in the NDSA community for having started the LOX program through Stanford University. Before coming to Stanford, David worked at Sun Microsystems, NVIDIA, and Vitria Technology. He currently holds 23 patents, and these days you can find him more often than not traveling the globe to discuss economic models for long-term storage. Kris Carpenter is the director of the Web Archive at the Internet Archive, where she works with national libraries, archives, and universities to provide technical expertise and services in web archiving and web search. For the last 15 years, she has divided her time between the online consumer and business-to-business services and software sectors. And finally, Krishna Kant is both research professor at the Center of Secure Information Systems at George Mason University and program director in the Computer and Networks Systems Division cluster within the National Science Foundation. Previously, Krishna worked for Intel on future server architectures and technologies, and he currently allocates his time among researching sustainability and energy issues in data center designs, cloud computing, and internet infrastructure. So after their brief presentations, we will certainly open up the floor for an extended Q&A discussion. So, David.
Okay. Thank you. Two quick notes. As usual, the text of this talk will go up on my blog after the talk, so you don't need to take notes, and there will be links to the sources and everything. And secondly, I've got to apologize for reading the talk, because I'm getting to an age where my mind tends to wander, and I want to stay on track because we don't have much time. So, however much we would all like to be environmentally responsible in our digital preservation activities, It's an unfortunate fact that, that reducing our energy demand isn't the biggest problem we face. As the Blue Ribbon Task Force on Sustainable Digital Preservation and Access pointed out 3 years ago, to no one's surprise, the big problem is economic. No one has the money to preserve even the stuff they think is a high priority. The only way that funds for preservation can be justified is by a commitment to provide access. So the research into the historical costs of digital preservation can be summarized by this rule of thumb. Ingest takes about a half, preservation, mainly storage, takes about a third, and access about 1/6 of the total. How much of the storage cost does power represent? So let's take a Seagate 4 terabyte drive, which has a retail price of $170 and a typical operating power draw of 7.5 watts. And the current Palo Alto Utilities small business rate, which is about 13 cents a kilowatt hour. Assuming it was operating for the whole of a 4-year service life, the disk power would cost about $35. Backblaze uses 45 similar but more expensive Hitachi drives to build its storage pod 3.0, which has dual redundant 760 watt power supplies. Assuming that the pod can survive a power supply failure with all the drives operating, the drives would take 337 watts and the rest of the system 422 watts, or a total of about 2.25 times the disk power alone. So the drive's share of the total system build cost is $213 odd. With its share of the system power, the drive would use over 4 years almost $79 worth of power, or 27% of the total 4-year cost. So as you can see, power is a significant cost of preservation, but even if disk is the only medium you're using, it's probably only about 10% of the total. It's about 1/3 as important as the cost of the disk media. So eventually, power is going to become a priority. Kreider's law, the exponential increase in disk density, used to mean that you could grow your collection 40% a year at approximately constant power. About 3 years ago, it became clear that Kreider's law was slowing. Now even the industry's optimistic projections are for no more than 20%. Many archives grow more than 20% a year. The more they do, the more their power costs will increase. So although demands for computation during ingest can be high, they're over quickly and don't contribute much to the energy demand of long-term preservation. And we have a very low energy way to store data. We write it to durable offline media and put them in a salt mine. But this doesn't provide usable access, and it raises awkward preservation issues about media obsolescence and integrity verification. Well, we can get a little bit of access by putting the offline media in robots, which is actually a lot less safe than a salt mine. But the robot infrastructure uses energy all the time, and the exponential increase in storage media density means that we don't keep the media for their theoretical life, but migrate, using energy, to newer media when they're no longer dense enough to justify their slot in the robot. But increasingly, as the first talk today pointed out, the Access Scholars want is keyword search and other forms of data mining. Robots full of offline media can't support this. So a recent paper on characteristics of low-carbon data centers shows that the key to reducing power consumption is to use the servers efficiently, assigning and migrating tasks to keep the power-up servers fully utilized and keep as many as possible powered down. While it's easy to migrate tasks among servers to keep only a fraction of them powered up, this just isn't practical for storage. Even before the demand for search and data mining, research showed that there were very few hotspots in the access patterns to preserve data. Search and data mining will spread access fairly evenly across the entire collection. This is likely to raise both the proportion of cost attributable to access, more than 1/6, and the proportion attributable to power. So to satisfy the demands of scholars, at least one copy of your preserved data has to be on disk or some other medium with equivalent access latency and bandwidth? Can we design a storage medium that provides rapid yet energy efficient access together with very low energy usage through time? So in 2009, a team from CMU showed that a fabric consisting of a very large number of very low power CPUs, each with a fairly small amount of flash memory, could answer key value queries at the same speed as conventional servers using 2 orders of magnitude less energy per query. They called their architecture FAWN, fast array of wimpy nodes. It worked well because the key value problem parallelizes well, and because the I/O performance of the wimpy CPU and the flash memory was actually much better than disk. So in 2011, Ian Adams, Ethan Miller, and I showed that if the lifecycle costs were properly accounted for, a similar approach could be cost competitive with disk for long-term storage, despite the much higher initial cost of disk. It would provide rapid access with a much lower energy demand. We called our architecture Dawn, durable array of wimpy nodes. It worked well because of a series of synergistic effects that greatly reduced power consumption and led to a much longer media service life. Unfortunately, there's an important caveat, namely, if lifecycle costs were properly accounted for. The much higher capital costs of Dawn are balanced by much lower running costs over a much longer media service life than disk systems like Backblaze's. I don't know any institution operating a digital archive that has a planning horizon long enough to make that trade-off. Most operate on an annual budget cycle. Large savings in, say, years 4 through 10 are ignored. Now, Amazon, a company that's notorious for not caring about making a profit, does have a long enough planning horizon. It's one of the reasons that they dominate the market for web services and especially storage. So because your short-termism means that you aren't going to buy the initially more expensive, but in the longer term cheaper Dawn systems, vendors aren't going to make them. They have their own version of short-termism. They're very happy to sell you a product with a limited service life. Doing so is called planned obsolescence and has a long history. In the storage world, it's driven by Kreider's law. In 2009, I blogged about Dave Anderson's description of Seagate's investigation of the idea of a disk drive specifically for archival use. Technologically, it was easy. You could build a very reliable, very long-lived drive, but there was no way to make money building it. One reason was that customers wouldn't buy it. The economics for them of replacing older drives with newer ones that were identical in all respects except for greater capacity are irresistible. The other reason was that even if customers did want to buy these drives, they would be a niche product sold in small volumes, so they would cost a lot more per byte than the consumer drives. Customers are, with good reason, skeptical of manufacturers' claims for reliability. Thus, even if the special archival disks actually did repay the additional cost in greater reliability, it would likely not be possible to persuade the customers of this. Of course, as Kreider's law slows down, it makes sense to keep the drives for longer, but it slows down slowly, never providing at any one given time a big enough motivation to invest the extra up front to get the lower running costs out to the planning horizon. So the pessimistic conclusion is the bulk of preserved data is going to be on hard disk, burning more power than it should for a good long time. Economics means that even that dramatic technological change, even if it can reduce power consumption by orders of magnitude, isn't viable in the marketplace. This is both because power isn't yet a big part of the total cost of preservation, and because institutions systematically discount the impact of future costs. Nevertheless, there are things that you can do while we wait for the dramatic technological change that can reduce your power consumption. They won't make a big difference, but every little helps. And this is where I hand on to the people who are trying to do that.
I may just remain seated, is that all right? I, too, am going to use notes for a couple of different reasons. I have a lot of very detailed information that I would love to share with you as part of the Internet Archive use case that I'll get into in a few minutes. And I didn't want to misrepresent any of the specific details. And I think I got this a little too close to my face. space there. Before I begin, I wanted to thank one of my colleagues in the Internet Archive operations team, a gentleman named Ralph Mullen, who was able to compile the statistics associated with the data I'm going to share with you. We thought it was important to provide a perspective from practitioners sort of rolling up our sleeves in the field, trying to deal with some of the challenges associated with data at scale and ongoing power consumption. So I think amongst cultural heritage organizations, motivations for green digital preservation and sustainability often never emerge or are driven by a wide range of factors distinct to an institution's mission, mandate, operating budget, the amount of control they might have over IT decisions, and the overall social political climate in which that organization operates. Maybe it doesn't.
I think you're out of range.
I'm out of range, sorry. I'll stand. All right. As David's already highlighted, green digital preservation usually isn't at the top of the list of issues facing a library, archive, or museum. Keeping pace with the rate of digital data ingest and its creation can be daunting enough. Motivations to preserve in a sustainable way vary depending upon where you are in the globe, how long you've been ingesting born digital content and digitizing physical assets, how rapidly your digital collections are growing, and the range of preservation and access services you support to those collections. There are limits to what any institution can achieve alone, or even in partnership with other like-minded institutions. But eventually, every organization or program faces a challenge that could include a green choice as a solution. Many of us in this community tend to be attracted to the promise of preserving more content and making more data accessible for the same investment of resource. Reducing overall power consumption is not yet a requirement we face. Doing more with the same amount of power, however, remains a seductive option. Of course, for some organizations, the reputation as an environmentally responsible institution can also be a driver, especially if you're investing tens of millions of dollars in green stacks. It makes complete sense to attempt to do the same with virtual collections wherever and whenever feasible. For centuries now, memory institutions and cultures have engaged in preservation of their sacred texts and objects using what we now term green techniques. For example, hiding them in mountain caves or salt mines, placing them into berms that seem to disappear into the side of a hill. In some corners of the globe, modern digital stewards are doing the same thing today. And I want to use an example of our colleagues at the National Library of Norway, who opened a mountain vault about 10 years ago now. They had in mind both physical and digital collections when they created the vaults and built isolated server rooms deep within the mountain to take advantage of naturally cool conditions and simply added ventilation to remove the heat produced by spinning drives. They've since had to tackle some issues with humidity, but none of those have impacted their ongoing operations. They also maintain one copy of all their data on a spinning drive today and 2 copies on tape. One copy of tape is actually based in Mo i Rana, the other's in Oslo. In the event of data loss locally, they can restore content within minutes. And the Oslo copy is really serving the purpose of disaster recovery in the event of a total catastrophe in Mo i Rana itself. They're also considering putting an additional replica outside their national borders. Now, this is a really robust example of a memory institution that's been able to lower their long-term cost of data and still provide a significant level of access. And they have well over 4 petabytes of data now sort of assembled within this infrastructure. But in general, that is not the case. You're going to find a trade-off between sort of lowering your costs and being able to continue to sustain your access. Or you're going to have some impact to the amount of time it takes. And many of us are using techniques to try to address this, like those listed on this slide, but they're trade-offs, no matter how you frame them. Now, there's also much we can learn from other sectors. Whether we're talking about cloud computing providers, local governments, businesses, higher ed, and high-tech for-profit and not-for-profits, many of these organizations are supporting extensive digital collections and service operations. And although individual case studies vary, the enhancements that many of those organizations have been able to implement are still applicable to cultural heritage, even though they're often optimized for real-time access versus long-term storage and access. Things like innovative physical data center facility designs and cooling systems, relocation of data to different geographies, increases in storage densities and improved airflows, increased average temperatures in server rooms, sometimes in excess of 85 degrees. Some examples of commercial efforts that you might want to take a look at that have emerged in the last 3 to 5 years are Yahoo's Chicken Coop data center model up in New York State, Google's data center in Hamina, Finland, or some of the evaporative cooling techniques deployed at Facebook, Google, and Yahoo. Now, a consortium of interested parties called the Green Grid, not unlike the NDSA, actually, in its structure, has been defining a body of standard metrics by which to measure usage and efficiencies in data centers, including things like power usage efficiency, server compute efficiency, data center compute efficiencies. Now, PUE is the only metric I'm going to speak to in any detail today from the body of those. And it's defined as the total energy needed to operate a facility divided by the energy needed to operate the IT within the facility. Now, the industry average PUE in 2008 was about 1.5 to 2, meaning for every 100 kilowatts of compute power, 50 to 100 kilowatts of cooling power were also needed to support those operations. Now, often organizations who embark on efforts to try to reduce their PUE are initially motivated by what it can mean for a reduction in operational expenditures. Meaning, maybe an increase in overall capacity for the same cost, or the operation of services at a fraction of the cost relative to another equivalent facility due to sort of the methods implemented. These are the very same motivations that drove the Internet Archive in recent years to make modifications to our data center operations in San Francisco. So I'm going to drill into those now. For those of you not familiar with IA, we're a digital library established in 1996. We're a not-for-profit that maintains over 14 petabytes of publicly accessible data, digital content, including ebooks, digitized text, films, video, audio, software, internet content, television news. I'm going to offer some limited insights into what making green choices might look like for an organization on a relatively small budget and with limited staff. But keep in mind, we tend to be a little bit wacky. Some of the things that we choose to do, others might go, oh my gosh. So think of this as sort of inspiration and directional opportunities to experiment with something different. So we began under pressure to lower our operational expenditures by reducing our power consumption. This came as a mandate in 2010 from our founder, Brewster Kahle. We had recently moved into the building that you saw pictured recently, and we really wanted to operate differently and in a more sustainable fashion. So the key metrics we identified to drive sort of evaluation of our processes was certainly improving our PUE as defined by the Green Grid and broader tech communities, and reducing kilowatts per petabyte required to support storage and access services to our digital collections. We've already talked about PUE, but I want to spend a quick minute on kilowatts per petabyte. Now, operation costs have been the second highest in our budget behind human resources for our entire history. The kilowatt per petabyte metric is a good way for us to measure our needs and to estimate budget implications for operational choices we are making at any given point in time. So it's a metric we've tracked since 2004, so we have a little bit of historic context that we can bring. Now, I'm going to spend just a minute going back in time and giving you a little bit of context in order to understand why we made some of the modifications that we did as of 2010. Now, we don't have any data prior to 2004 other than CapEx that we really tracked on an operational layer. So we're going to start our history in 2004, even though our operations go back to 96. So from 2004 to 2010, we rented traditional air-conditioned data center facilities, much like what many of you might be familiar with. We replicated data locally and globally to foster distributed preservation, and we designed and built our own hardware to reduce power consumption and minimize the risk of data loss, biasing longevity over compute capacity. In fact, we cooled drives instead of processors in individual nodes. Now, the upsides to this approach was PUE fell within industry averages, as best as we could estimate, at around 1.8 in 2010. This was largely due to increases in storage density and some of the increase in component quality without increases in requirements for kilowatts to operate individual components that occurred during this same time frame. In fact, over 2 to 3 generations of hardware migration, we were able to reduce from 117 kilowatts per petabyte down to 39 kilowatts per petabyte, not including cooling. And that's all for the same stable upfront investment of about 120K USD per rack. Now, the downsides is due to the rental arrangements, we had no real control over power consumption in aggregate and optimization of that, nor cooling and airflow in our individual facilities. And by 2010, we'd done everything we could do to optimize hardware. Now we needed to try something different. In 2008, toward the end of this phase of our operations, we actually partnered with Sun Microsystems, this was pre-Oracle days, and deployed one of the first generation of modular data centers at one of their Santa Clara facilities. The promise of this was that it would be cheaper and faster to build out than a traditional data center, and it was. But PUE for the installation was estimated to be at the high end of the range of the industry averages at the time, at about 2. We estimated the kilowatt per petabyte requirements at 67 kilowatts per petabyte, and subsequent generations of containers had better ratios due to higher density and hence lower kilowatt per petabyte factors. Cooling was water-based, though, so when it came time for us to relocate the container under a request by Oracle from Santa Clara to Richmond, California, we were unable to do so. We actually joked internally that if only we were operating a swimming pool, then we could make a green cost justification that we'd heat the pool and cool the data center. But alas, we don't operate a swimming pool. In 2005, we also began experimentation with cloud computing on Amazon Web Services to facilitate data mining and indexing of web objects at significant scale. We've retained, on average, about 30 terabytes of data over a 7-year period in S3 with no data loss or corruption. We could not afford at the time, because we weren't able to make the data public, to sustain the model at petabyte scale, but the cloud continues to represent on-demand resources for us for hosting research data sets and for supporting large-scale computational needs without investment in additional infrastructure. Our largest jobs tend to run for about 24 hours on thousands of nodes at a time, but that's become a small job on Amazon, if you can believe it. So the next set of experiments really came to fruition, as I mentioned, in 2010 when we moved into our Funston Avenue facility. Now, that's a historic Christian Science church constructed in the 1890s in the inner Richmond district of San Francisco, which is pretty foggy most of the time. And then for the first time, we had complete control over our physical plant. However, we were handed a set of rules that we had to operate under in order to modify our facilities. Specifically, we were to make a concerted effort to reduce power consumption by measuring actual usage, analyzing and evolving solutions, not by guessing, which sounds simple, and of course, that's what you'd want to do, but there's always a caveat when you try to implement these things. Racks needed to coexist with humans. We didn't want to hide them. We needed to make sure we weren't ruining the historic space with ducts and AC plant. In fact, there was a mandate for no air conditioning whatsoever, since we're 2 miles from the ocean with 49 weeks per year of natural cooling. We also decided it was time to use commercially manufactured equipment. We should not continue to assemble our own hardware. We needed to focus on core missions. We needed to make it as pretty as the Jedi Library. So on the hardware front, we were able to acquire commercial off-the-shelf servers, although we did make some modifications to them. We ended up removing some server fans, slowing remaining fans. We dampened wall covers, and we ended up repurposing heat to actually heat our building operations. We're using Supermicro on the manufacturing side and Kingstar for assembly and local support. In parallel, we were handed the mandate across the Internet Archive to ensure that we were deduplicating all materials upon capture or creation prior to ingest into our catalog systems. So there was a massive effort to deploy an HBase implementation, for example, to ensure that we were for ongoing crawling, everything was deduplicated in real time. In terms of the other mandates, we also looked historically, like, should we go back into our existing data sets and deduplicate back through time? We determined that actually it was going to cost us more resource than benefit, so we did not actually deduplicate back. And anything written prior to 2010 is as it was originally written and contains a fair amount of duplication in our collections. Now, we hit a series of pitfalls along the way. You probably can't read this, but when you go to look at the slides later, you'll love this Dilbert. It's absolutely hysterical. Our biggest issue was the power company. There were smart meters deployed. They were collecting real-time data over a network, but they'll be damned if they'd give us access to an API to our energy data. So we faced the problem of, well, how do we actually take measurements ourselves, and how do we afford to do that? Most of the available solutions were beyond our budgets at the time. So Ralph, who I mentioned earlier, a senior member of our ops team, actually built a whole data center real-time networked power meter for less than $500. He plans to write up and open source the instructions for how he accomplished that, so other institutions can do the same if you're interested. Once we'd stabilized the physical infrastructure and collection data management policies, we turned our attention towards server efficiencies in terms of timing energy use to avoid peak utility windows. We also wanted to make general improvements to our productivity per server mode. The image, which you can't really read on the left, shows an example from monitors of our web crawl and index merging operations. The first spike you see is a compute job. We were able to change routines to smooth out usage and avoid repeats of those intervals. The second spike is an incident of weather, specifically an increase in outdoor temperature. Sometimes we can increase natural airflow and reduce temps as they rise. Reduce temps internally as they rise externally, but about 2 to 3 days per year we'll get external temperatures in excess of 90 degrees, and usually they fall in a row, unfortunately. And there's really nothing we can do in these circumstances. So it is actually our official policy that if we believe our equipment is at risk, we will actually shut it down. And in this case, green preservation trumps access. Now, this is only one replica of our collections. There may be another data center within our network that might pick up publicly available access, or you'll get the friendly message explaining that we're unavailable for a period of time. Now, the other thing that we were, the one on the right is actually showing a series of Hadoop jobs. So I'm going to, I only have 2 more slides, so I'm going to go a little bit faster. In terms of some of the other things we were able to put in place was more sophisticated automation to manage environmental change. We combined software with network devices to measure and monitor and make data-driven adjustments, both virtually and physically. And this is an example. For example, we can look at, if there's temperature and whether or not a fan is actually operating, then power up an alternate fan and alert the humans. That type of logic is now widely distributed within our infrastructure. Now, the good news is we've seen pretty substantial success over the past 3 years. PUE is usually less than 1. Heat gets reused within the building. Not all days do we attain this level, but we do so. We violate this at our own discretion. The kilowatt per petabyte metric has dropped from 8.5 to 2.8 kilowatts per petabyte. You can add about a kilowatt if we're running compute VMs, and we do so on most nodes, but not all. We're not going to expect many additional efficiencies in hardware optimization. We're really looking at other ways of greening in the future. Our data centers operations are quiet. In fact, we hear more complaints about the loud human nearby or the fact that there's no place to make a phone call than we ever do about our servers. And I wanted to leave you with one more wacky thought. So one of the members of our ops team sent me a reference to this project, more as a joke than anything, but I thought it was kind of a fun way to close out this talk. If you haven't heard about Server Sky, it's a concept around putting data centers in space in sort of little microcosms, proposed by a guy named Keith Lefstrom up in Oregon. And you know, especially in context of the raging debate about putting solar planners in the desert, it seems relevant that we might avoid the debate altogether by just launching out into space. Thanks.
Okay, good morning. So one of the advantages of being the last speaker is that most of the things have already been said here. So I will not bore you with the stuff that's already been said. Instead, focus on some of the new points that perhaps need to be brought out. Okay, so I'm going to be talking about sustainability. So there's obviously a natural conflict between sustainability and preservation. So in some sense, I'll be talking not so much about preservation, but how you can get away without preserving in some sense. Okay. So let's see. All right, so preservation obviously has a significant environmental footprint, and some of those things have already been talked about. There is an issue of storage media life, because disks, for example, last for 3 to 4 years. You have to replace them. And what do you do with all the garbage that you generate? There is obviously the question of housing and access management of the media. There is that robot that you see there picking out the tapes. And then, of course, the data centers, which you need for processing and for online storage. Okay, so let me start out by asking the question, what do we want to preserve? Most certainly, we don't want to preserve data. We want to preserve information. We want to preserve data that is useful. In fact, what we would ideally like to preserve is the knowledge. Of course, the real challenge is how do you preserve knowledge or the kind of knowledge that you might need to derive without preserving the raw data. Okay. Now, you can do that to some extent. You can throw out parts of the data that are not interesting, but in general, that's a huge challenge. Okay, so I'm going to talk about 3 sustainability issues. So first of all, as has been talked about many times this morning, that it's not enough that you just store the data. Well, the real value of the data is what you can do with it and what kind of insights you can gain from the data. And therefore, the processing is very important. And as a result, if you're talking about sustainability, you want to reduce the environmental impact of the data centers. The second one has to do with the data itself. If you look at the data in the wild out there, there's a lot of junk there. And the question is, can we get rid of that junk and preserve only what we really need to preserve? Okay. And the third one is, there is obviously a trade-off between keeping everything and processing everything from scratch versus you keeping partially processed data and perhaps not necessarily the original data. And there are obviously sustainability trade-offs in terms of computing impact versus the storage impacts and so on. Okay, so you've already heard a lot about data centers. I will not spend a whole lot of time on data center. In particular, I will not talk a lot about the power aspect of the data centers. We already know that the data centers consume about 2% of the total electricity. A lot of the power gets wasted, and so on and so forth, and it continues to increase. However, that's not the only aspect that we need to worry about. In addition to power, well, data centers are physical entities. They use a lot of materials. They use a lot of water. There are manufacturing costs. So if you look at data centers in terms of their overall environmental impact, for example, the carbon impact, well, there is a lot more impact than just the energy that you consume in processing. And that's why it's a good idea to not just look at the energy, but look at the entire environmental impact of the data center. Okay. In fact, the energy itself really does not matter. It's so much, what really matters is the carbon footprint. Imagine for a moment, let's say that your data center was being entirely operated on renewable sources which had low carbon impact. Okay. In that case, well, it's not so much how much energy you use, but ultimately how much is the carbon impact. Okay, let me give you some quick examples. So if you look at the power distribution infrastructure in a data center, starting from the transmission lines all the way up to the point where you can actually use the power, well, there is a lot of infrastructure there, and it has carbon impact. Okay, and what if you could reduce that? And so there is this idea which is being investigated quite actively these days. My research also includes that, which is that use the renewable energy as opposed to just using energy from the grid. Well, what are the challenges? The renewable energy often is variable, and therefore there might be times where you don't have enough energy available. Then what do you do? So to do that, well, you need some adaptation. You should be able to adapt your data center to the available energy. Cooling infrastructure, again, huge environmental impact. So as already been talked about, then you operate the data center without any cooling. You operate them using your ambient air, for example. But that, of course, has a challenge that there might be things that might be overheating. And as a result, you cannot do all the processing that you want to do. So there is a question of adaptation there. Okay. Over-design. This is another topic that's often overlooked. We love to over-design things just to be safe. So for example, if you need 1,000 watts in your server, you will probably buy not a 1,000 watt power supply, but probably a 2,000 or even a 3,000 watt power supply, just in case. And what happens when you do that is that you are operating a lot of these devices and systems at much lower utilization than their full capacity, and they tend to behave very, very inefficiently. So for example, a power supply, when it's operating at 20% of its capacity, will probably give you only 50% efficiency. Whereas if you were to operate it near 80% of its capacity, it will be more like 85% efficient. Okay. Okay, so again, if you were to cut down this over design, then you need adaptation for periods where you run out of capacity. Okay, so this led to this notion of energy adaptive computing that I've been looking at for the last couple of years. And the idea is that you replace over design with the right sizing along with a smart adaptation. And there are many instances of this. You can do this within a data center. You can do it among clients. You can do it for the entire infrastructure. There are a lot of challenges in being able to do this. Obviously, you want to be able to maintain the processing and the quality of service requirements, and at the same time try to minimize the carbon impact. Okay, so that's all I'm going to say. I will not bore you with any research results. There are a lot of results that are available. Some of the papers you can see on my website. But basically, that's the whole idea that we have been looking at for the last couple of years, that if you look at this from this energy adaptation perspective and coordinating the use of energy across different systems and subsystems, you can actually significantly reduce the environmental impact of processing. So let me switch over to another topic. Again, a topic that has been talked about. The data has been growing, obviously. And it's not only the data generation rate that has been growing, but also the total amount of accumulated data has been growing at an exponential rate. Okay. However, if you look at this data, what turns out is that more data you have, you perhaps have more junk in that data. So the amount of useful information, okay, that you have in the data is going down. Okay. And what can we do about this? Well, first challenge is how do you define what is useful? Okay. It's always a challenge. But still, there are a number of things you can do. Now, along with that, there come challenges in terms of increased power consumption, all the disk drive that you need to throw out, and then the cumulative impact, because people, once they store the data, they don't want to delete it, okay, which is not sustainable. Okay, so there are a number of opportunities, data reduction. You have opportunities within individual objects, objects being your web pages, files, databases, and so on. You have opportunities at the level of your administrative domain, which could be your house, your office, your business, and so on, and all across the administrative domains. Okay. So there are a number of options available. Compression, compressive sampling, basically keeping the samples that you really need. Delta encoding, if you already have some old data, what is the difference from the old data? Very often people bundle the VM along with the data so that all you have to do is just transfer that somewhere and start running the VM. So there's a lot of duplication there. You can do a lot of deduplication across the objects within administrative domain. Of course, across administrative domains, it becomes a lot more challenging. Okay. Now, in doing all of this, there are a number of trade-offs. There's a trade-off of storage versus data movement, which takes energy and, of course, time. Moving petabytes of data is not easy. In fact, you don't want to do it. And versus processing. There is issues of fidelity versus cost. You could have reduced representations, which will be more effective from a sustainability perspective, but then there's a question of what are you losing. Okay. And then there are issues of access, privacy, and security across domains. Okay, finally, I'd also like to talk a little bit about the role of the content creators, and we are all content creators. We all behave very badly. Okay, we can use some best practices to really reduce the growth of data. So we just take a file and just blindly send it to 10 of our friends, and they just download this file and then forget all about it. Whether or not they need it, that file is always there. Okay, so that's something that I guess we as content creators can address to a large extent. Purge obsolete data, defective data, unneeded data. And then finally, the issue is of metadata, and that has been talked about this morning. Well, in some sense, metadata is more important than data. But there might be standards for metadata, but most people don't bother. Like it was said in the morning, that they will just fill some of the entries and not really bother with it. And that really reduces the value of the data and the value of preserving the data. Okay. And that's the end of my presentation.
Well, is this on? Well, I want to thank all of our presenters one last time, and I think we do have some time for Q&A, and I will just sort of kickstart the conversation, but then I'm going to hand it off to all of you to pick it up in whatever direction you would like to take it. So I think actually, Krishna, I think you raised some of the most complex issues for, I think, that are on the minds of a lot of people in the room in terms of how do we value our data, and how do we assess it? How do we think about issues such as selection and perhaps even reduction of our digital collections? So I wanted to give Kris and David an opportunity to kind of perhaps respond to some of those issues, and perhaps that will kickstart us.
We've had this conversation before. I drew a graph showing the effect of the IDC's projected 60% a year compound growth in data, and the 20% projected cost of 20% CRIDA rate, and the 1% projected growth in IT budgets, which projected out that if this is true, then 10 years from now, storage is going to be consuming everyone's entire IT budgets without anything for processing it. So we've been lulled into a false sense of security by the very high CRIDA rates in the past. And storage going forward is going to be a lot less free than it used to be. And so we are going to have to take some tough decisions about what we decide to keep. And it's better to take those decisions up front than run into the wall and then have to spend money to get rid of data that you can no longer afford to store because you don't have the money.
So I think in terms of, I'll use one example in sort of our web-wide crawling context. We actually went so far as to hire a body of interns, college students that were willing to go in and look at the highest, most sort of data volume intensive resources that we were crawling to confirm which fell into certain categories of content versus others. And we took the top, I think it was 20,000 resources. And we did that because there's some subset of content that ends up being mirrored in lots of corners of the web. And we can get a representative sample of that type of material and what the web was like today from a researcher's perspective, but we don't need to have all of that from every resource. So we're trying to come up with innovative methodologies to start to pare down and still have representative samples of everything that's out there that can be aggregated together, but not go so far as to suggest that we're covering everything at all depths and all breadths.
Questions in the audience?
Let me make one point here. So I guess when we think about raw data, there is this somewhat of a religious idea that we need to keep the raw data all the time. And that's not necessarily the case. Now, you could always come up with a counterexample that if you filtered the data in some way, then someday somebody will come up with a question that you could not answer. And that becomes a kind of a fear. And because of that fear, we say that, okay, let's not worry about it. Let's just do preserve the raw data, and then we can do the deep learning on it for whatever that we need. I think we have to somehow get away from that mindset. And start thinking about, given the type of data, what are the interesting kind of questions that one could possibly ask? Now, I know that's not something that can be easily characterized, but we need to go in that direction and ask those types of questions, perhaps build some models as to how we can perhaps capture, at least in a theoretical sense, that if we keep maybe say 25% of the data in a particular way, then you can answer maybe 99% of the questions. And if you can get there, even approximately, I think it will be a huge progress.
Yeah, I'd like to reinforce that. If you look at what the really high data rate scientific experiments like the Large Hadron Collider or the Square Kilometre Array and so on, they do massive data reduction before they store anything. Mm-hmm. And that's for two reasons. One of them is they can't buy the storage bandwidth that they need, and the other is they can't afford to keep that stuff for long enough to be interesting. And so in those fields, that's already happening. it's much less easy to do that in the humanities because you don't have that depth of understanding of what the data really is. But at the same time, what we see this morning with the Crumb and Crawl talk and what the Internet Archive's doing is that in the humanities, having a random sample of what's going on is often as useful and as having the whole thing, and almost as useful. And this is actually the tradition with archival materials. Archivists normally collect a few % of the stuff that arrives in boxes. And we need to translate those techniques into the work that we're doing in the digital space, because we are not going to be able to afford to keep everything. And there are no technological fixes for that on the horizon.
So where would you, where do you see the gaps in our sort of R&D knowledge? Like where would you like to see the field go in terms of addressing some of these issues? It sounds like there's some consensus here on the stage about thinking about the ingestion of data up front, perhaps automating that ingestion, sort of conducting the selection at that early stage. Where, you know, there's a whole room full of preservationists here, and where do you think that you know, some of those areas could be examined and researched further?
Having worked for industry, I would say that you always start with the requirements. Mm-hmm. And if we can specify the requirements in terms of what kind of fidelity do you need, for example, or what are your requirements in terms of what is it that you want to preserve. And I suppose the answer is not that you want to preserve data, as I said earlier. The answer should be that you want to preserve something derived from the data, some sort of a knowledge. Can we specify that? And I don't think right now we have the mechanisms to really even talk about it in an intelligent way. But can we begin to talk about it, about these requirements, have a language for expressing those requirements? And once we are there, then perhaps we can think about how do we take those requirements and then work backwards and come up with techniques which will be able to reduce the data and still preserve those requirements.
And I think there's a little bit of a chicken and egg problem. I mean, Lisa pointed this out this morning, that we're so focused on collecting and storing and preserving. We don't always have the benefit of putting the compute capacity close to our storage and mining and analyzing at a machine scale that gives us insights into what else we might do differently. And I think many of us operate a little bit from a place of fear. Well, I better keep that because I have no idea when I'm going to be able to put it in a useful spot and somebody might do something amazing with it. So I do think, to the extent that we can invest in the discipline of data science as a community and really foster the development of that type of scholarship, make our archives available, if not within our own four walls, but outside of that, in contexts where researchers can have more interaction, I think we'll learn immense amounts about where we need to go from here, and hopefully get out of this cycle of, well, we darn well better preserve everything because we don't know what we might want to do with it later.
Well, I think that's a good place to end on. So I'd like to thank our presenters one last time, and I'm sure they're going to be around for further questions. So feel free to come find me or one of our presenters if you have further questions.
This has been a presentation of the Library of Congress. Visit us at loc.gov.